So with that, not waste further time and project talk and welcome Supratim. So just tell me to advance and I will advance and we'll go from.
Sure. I'm facing a bit of a problem in hearing your voice. It's breaking up.
Oh.
It was breaking up from time to time, but I hope
Okay.
I am audible. And,
you are audible. Let me change my location as we discuss, so you can get started if you can.
Yeah.
Okay.
Sure. So thank you for the introduction. I have attended many of the talks in these series that have been given by so many distinguished speakers, and it is indeed a privilege to be able to contribute to this series. I'll be talking about work that has been done by masters and PhD students, most of them former masters and PhD students. And I'll break this talk up into two parts. The first part will be based on work done by Spandan, Pratik, and Shumit. And Spandan and Pratik were the main drivers of that work. And as you can see, all of them have moved on to greener pastures. And the second part of the talk will be based on work done by Anuran, who just finished his master's thesis from IISER Kolkata. So next, please. So the conundrum posed by cooperation can be stated in very simple terms. Altruistic behavior comes at a cost, but selfish behavior does not entail any such cost. And since altruistic behavior is costly, it translates to lower fitness for the altruists. And according to the Darwinian paradigm, a competition between altruists and selfish agents over time will gradually lead to the elimination of altruists from the population, and eventually the entire population will only be inhabited by selfish agents. So this is the conundrum that is faced, and which begs the question, how do we explain the survival of altruistic agents? Because altruism is indeed observed all over the natural world. So, next slide, please. And so Darwin himself was aware of this problem when he published The Origin of Species, and especially in the context of social insects like honeybees, where there is a class of bees called the worker bees who are infertile and who do not reproduce, and does most of the work to maintain the colony. And so these kinds of systems posed a huge challenge to Darwin's theory. But even before Darwin, this aspect of human behavior has been debated by philosophers over the ages. And one striking quote that I came across was one by the English political philosopher Thomas Hobbes in his most famous book called The Leviathan, who argued that every man is in a perennial state of war with every other one, and the life of man is solitary, poor, nasty, brutish, and short. And despite such rather dire and pessimistic views of human nature, cooperation is pervasive, and in fact, it is essential for the formation and survival of any social unit. And so how do we explain the emergence and sustenance of cooperation? And in this context, evolutionary game theory provides a useful framework for understanding the dynamics between altruists and selfish agents. And evolutionary game theory essentially deals with evolution of population with frequency-dependent selection. The idea is that the fitness of an organism, it is not just an intrinsic property of the organism, but it also depends on who that individual interacts with in the population. So for example, the fitness of a deer on the picture, if you see the picture on the left, when it's interacting with a herd of other deer is going to be very different if a leopard compared to the situation where a leopard enters the scene. And so the fitness becomes dependent on the frequency of the different types of individuals that make up the population. So next slide. So even though I'm interested in cooperation in human societies, cooperation exists and is observed across all biological scales. And I'm going to demonstrate that by giving 3 examples. More than 4 billion years ago, before the first live cell emerged from a primordial soup, sequences had to figure out a way to replicate, produce more copies of themselves. So you have to keep in mind that during that epoch, there were no transcription, translation, regulation, all the complicated machinery that a modern cell uses to reproduce. There were not even proteins. We are talking of an epoch when proteins could not be synthesized because the protein synthesis machinery had not yet evolved. And the sequences at that time were mostly made up of RNA. And so the way the sequences replicated was that they had to find a template. A template is a sequence which is shown at the top here. And across the template, the nucleotides which would be available in the environment would come and get attached according to Watson-Crick pairing rules and build up the sequence 1 nucleotide at a time. And if you click on the next slide, yeah. So this is how 1 nucleotide keeps getting added across the template, and this builds up the entire primer. And when that primer is built up, it separates from the template and becomes an RNA sequence in its own right. Now, the problem is that while this is a useful method for replication, we do need templates. Whereas the replicators, the selfish replicators, do not often act as templates. So a class of replicators could evolve which would utilize the other sequences as templates. And because by doing so, they could replicate much faster, those selfish replicators would keep increasing its numbers at the expense of the templates. And we would end up in a situation where there were no templates to be left in the population anymore. And then all replication process would stop to the detriment of everyone. So this is an example where in a prebiotic scenario, this competition between selfish replicators which do not act as templates and replicators which do act as templates can lead to interesting consequences for the origin of life. So in the second example, next, yeah, we can think of a bacterial colony which consists of 3 different strains. One of them is an antibiotic producer, shown in red. Another is a non-producer, which doesn't produce the antibiotic, but it also is not affected by the antibiotic that is produced by the producer. And there's a third strain which is sensitive to the antibiotic and is killed off by the antibiotic that is produced by the producer. Now, in a 2-way competition between the non-producer and the sensitive has the largest growth rate and it can outcompete the non-producer. And in a 2-way competition between a non-producer and a producer, the non-producer wins again. So the non-producer is like a selfish agent because it doesn't have to pay the metabolic cost to produce the antibiotic, but it can survive if it is present in a population with producers as well as sensitive strains, because then it can take the advantage of the protection provided by the producer to increase its number. And interestingly, this coexistence of all the three different strains does not happen in a well-mixed population where there's equal likelihood of each of these strains to interact with one another, but it happens in a more structured population like the one shown here in a lattice where you have the different strains. So if you can play the video now, it'll become clear what I'm trying to say. So you can see that there are these three different strains which are competing with one another, and sometimes the number of one of them increases at the expense of the other, but eventually in the long time scale, all three coexist together, and this happens only in such a lattice structured population. And of course, finally, we see cooperation at the scale of human societies as well. And in the last example, you can see from the next thing where it shows an example of a hunter-gatherer society where if individuals cooperate together, then they are better equipped to hunt and forage for food and feed the tribe. Whereas those communities where there are a lot of selfish individuals cannot perform this job well, to the detriment of the entire tribe. So cooperation is observed across all scales, but for the purpose of this talk, I'll be focusing on cooperation in human societies. Next. Yeah. So over the last several decades, a lot of work has gone into understanding the mechanisms by which cooperation or altruistic behavior can be sustained. And there's a wonderful review by Novak, a somewhat older review in 2006, and a more updated one with Rand in 2013, which lays down the different mechanisms for sustaining cooperation. And I'll very briefly go through the list because I'm going to focus on one of the mechanisms in the subsequent part of the talk. So the first mechanism that's very useful depends on strategies which are reactive, where individuals react to actions of an opponent. And these mechanisms are called direct reciprocity, and one of the most famous strategies which allow for cooperation to be sustained and not be outcompeted by completely selfish counterparts is called the tit-for-tat strategy. So it essentially says that I'm going to be nice if my opponent is nice to me, but I'm going to be mean if my opponent is mean with me. And this strategy works remarkably well. And till about 10 years ago, a lot of work was devoted in trying to find strategies which are somewhat more cooperative than tit for tat, and yet can do better in a population consisting of purely selfish strategies. The other mechanism is called indirect reciprocity, where the interaction is not just based on reciprocating the action of the opponent, but there's an observer which assigns a reputation based on the action taken by an individual. So suppose I cooperate with you and a third observer is observing this interaction, that observer can ascribe a good or bad reputation depending on the action that I take. And that reputation builds up and can be utilized by other people to decide whether to cooperate with me or not. And such strategies are useful, but they depend on specification of what are called social norms, which are essentially rules which determine how a third observer is going to judge whether my action is good or bad. The third mechanism has to do with the fact that often the interactions in a population are more constrained. Anybody cannot interact with any other member of the population with equal likelihood, interactions are typically restricted to nearest neighbors. And so the structure of the population plays an important role in facilitating the spread or survival of cooperative strategies. And as you saw in the example of the bacterial community, in the well-mixed case, when all three different strains were present, the sensitive strain would win that competition because there's only one fixed point which corresponds to the dominance of the sensitive strain. But in a lattice-structured population, all three can coexist. So the underlying population structure plays an important role in cooperation. And then there's another aspect, which is the selection, when the unit of selection is not the individual, but the group. And that's because groups of cooperators perform better than groups of selfish agents. They are better equipped to perform tasks which require cooperation and so on. And finally, there's kin selection, which was developed by Hamilton to explain the behavior of social insects that I alluded to. And so next slide, please. Yeah, so what we see from these examples is behavior evolves during a social conflict. And that's why the title of the talk was Learning How to Cooperate, because all of us adopt certain learning strategies, and we need to identify what are the factors which affect these learning strategies and how do they collectively affect cooperation levels in the population. And so the different factors can be the structure of the network, the nature and behavior of connected neighbors, and even our own individual aspiration levels. And how do we incorporate these factors into learning strategies, and how do these factors collectively shape outcomes at the population level are two of the key questions that I will be addressing in this talk. So this brings me to the first part of the talk, where I'll focus on how the strategy environment and the wealth can affect cooperative behavior of individuals and how that plays out and affects cooperation at the level of the population. And to underline that kind of scenario, I'm going to make use of what's called a public goods game. So this is a game that's quite useful in framing, in understanding this problem of cooperation. So the game is as follows. So there's a public resource and individuals have to contribute for the upkeep of that public resource, which benefits everyone in the community. But sometimes a selfish individual can choose not to contribute. And by doing so, it can still get the benefit from the public resource as long as enough individuals do contribute for the upkeep of the resource without having to pay the cost. But if this process continues over time, other members of the population will start imitating that selfish individual because they will also find that it's more beneficial for them to stop contributing while enjoying the benefit of the resource. And if this process continues, the more and more members become selfish and they stop contributing, the public resource collapses to the detriment of all. So this is a well-known phenomenon called the tragedy of the commons, and has driven research in this field for several decades. Now, this problem can be formulated in simple mathematical terms. So every time an individual contributes for the upkeep of the resource, he has to pay a certain amount of money, but that amount of money everyone contributes gets pooled and then because the resource benefits everyone in the population much more than the amount contributed individually for the upkeep of the resource, it gets multiplied by a certain factor and then redistributed to the entire population. So in this framework, M is an amount of money that each individual contributes for the upkeep of the resource, and NC is the number of altruistic individuals, that is the number that actually does contribute in the community. And R is called a synergy factor, which is a multiplicative factor which gets multiplied whenever anybody contributes for the upkeep of the resource, because the benefit accrues to everybody in the population. So an altruist has to pay a cost, but gets a benefit which is significantly larger than the cost that she has to pay, whereas a selfish agent can enjoy the benefit without paying the cost. And in the course of the public goods game, each individual compares her payoff with a randomly picked member, and it can choose to imitate the member depending on how the other member's payoff compares with her own payoff. And if that payoff is greater, it can choose to imitate the member, and that's how selfish individuals can eventually take over. So next slide. So one of the key features in the public goods game is about deciding how individuals update their behavior or update their strategies over time. And in the conventional paradigm for strategy update, what's usually done is what I just mentioned, that two individuals are picked at random, and one is considered to be a focal individual, the other is a role model. The focal individual compares her payoff with the payoff of the role model, and if her payoff is larger than that of the role model, she retains her own strategy. If her payoff happens to be smaller than that of the role model, she can switch to the strategy of the role model. And in this way, selfish individuals have a better advantage, are more likely to be imitated by cooperative individuals if they have a larger payoff. And so the way it is done is through this relationship, which many of you would recognize as being reminiscent of the Fermi distribution function. So pi y and pi x are the payoffs, one for the role model and pi x for the focal individual. And beta is called the inverse of the selection temperature. So in the limit of very large beta, after the comparison, the role model just blindly imitates the strategy of the focal player blindly imitates the strategy of the role model if the role model's payoff is larger. So for finite beta, this introduces some stochasticity into the problem, and it allows the focal player to not just blindly imitate, but do so with a certain probability. Now, a drawback of this is that this method of strategy update, which determines the collective outcome in terms of the cooperation levels of the population, is that neither the strategy environment nor the relative wealth of the players are being considered in the process. It's just being done blindly when a focal individual picks a random neighbor. So this is what we decided to improve on, and we were motivated by this experiment that was done, which I'll describe in the next slide. Yeah, so about 6 years ago, this fascinating paper came out from the group of Nicholas Christakis, where they carried out these behavioral experiment using a platform called the Amazon Mechanical Turk. And so these kinds of online platforms have really transformed the field. All these experiments are done online. Participants are recruited online, and they are asked to participate in these experiments and given some money in return for their participation, and then the results are analyzed. So the experiment that the Christakis group carried out was to take a group of participants who were obviously volunteering to be participants in this experiment and made them play a public goods game of the kind that I described earlier, but with a slight twist. Now, each of them were connected in a network where every participant had on an average 4 connections. The average size of the group consisted of 20 participants, and all of them were given a certain amount of money. So this was the initial endowment, and the amount of money given was divided into 3 categories. In one case, all of them were given the same amount of money, which corresponds to an initial Gini of 0. So the initial Gini talks about the levels of wealth inequality in the population to begin with. So this was a formula that was used to calculate the initial Gini. This is a very standard index that is used in the economics literature, and even countries are assigned Gini coefficients to measure the level of wealth inequality present in the population. So the 3 different experiments started off by assigning 3 different initial Gini coefficients depending on the kind of endowments that were distributed to the different individuals. And then they were made to play the public goods game over a number of rounds. And but during the course of the public goods game, they knew in one scenario the actions of all the other members, whether the members cooperated by contributing to the public good or defected. And also they were aware of the wealth accumulated by each of the members in that group. Now, on the basis of this information, they were allowed to restructure their connections at the end of every round. So the network did not retain the same structure that it started off with, but was a dynamic one where individuals could acquire new connections with members that they were previously not connected to. And what they found as a result of doing these experiments was that if you plot the Gini coefficient over time, in a scenario where all the members were aware of the wealth of every other member in the community, the Gini coefficient tended to be much higher than the case where they were unaware of the wealth of other members in the population. So wealth inequality levels were lower in the invisible wealth scenario, which was a surprising result. And cooperation fractions were also higher in the invisible wealth scenario. So more people contributed over time in the invisible wealth scenario compared to the visible wealth scenario, where everyone was aware of each other's wealth as well as actions. So when we started to think about this experiment and analyzed it using the conventional pairwise comparison model, we found, as will be seen from the next graph, that the pairwise comparison model completely failed. Over time, the fraction of individuals who contributed went down to 0 and everything broke down. So this suggested that there has to be a more more than just pairwise comparison or blindly imitating somebody's strategy that is at play when it comes to individuals updating their strategies over time. And this motivated us to develop a new decision heuristic, which takes into account the effect of wealth as well as strategy in developing a new update rule. So if you can go to the next slide.
There is a question, Supratim,
Yeah,
from Shomin
sure.
Mitra.
Yeah.
Sorry, I don't know if I can't see myself, but I hope you can see me. So,
Yeah.
Supratim, I had a question about your last slide, which is
Yeah.
interesting. So, you know, a lot of talk and studies have come out of companies now about making company salaries be visible to all employees. I mean, traditionally they have not been. So do you know if any kind of studies have been done as to whether making them visible, all employee salaries visible to all employees, leads to some, I mean, the claims are whether it leads to higher or lower productivity, which I guess would tie to cooperation in some way?
No, the short answer is no. I don't know of any such studies, but I can get back to you. But yeah, this issue of wealth visibility has been going on for a long time. In fact, there's a country, Norway, which makes the income of every resident available in a public database, available to everyone else in a public database. And but one should not read too much from this experiment alone, because there are some subtleties. So later on, another experiment was performed where punishment was also included as part of this game. And then they found that in the visible wealth scenario, inequality levels are lower. So yeah, so this is not the whole story.
Okay, thanks.
Yeah,
Carry on.
so yeah, so this motivated us to go beyond the pairwise comparison model to try and develop a decision heuristic which takes into account both the strategy environment as well as the wealth in determining the likelihood of cooperation in a public goods game. And we were primarily motivated by papers written by Suri and Watts and Cote et al., where there were two different studies, one which showed that if you seed a cooperator, then the likelihood of contributions from individuals who are connected to that cooperator increases. And similarly, if you seed a defector, a selfish agent who does not contribute, the likelihood of contributions from those who are connected to that seed selfish agent decreases as well. So this suggests that the strategy environment does play a role in determining altruistic behavior. And the other paper was about how income inequality levels can affect altruistic behavior. They did experiments which suggested that high income individuals were likely to contribute less, especially in situations where wealth disparities were large compared to low income individuals. So both these behavioral experimental studies suggest that both wealth and the strategy environment can affect our inclinations to contribute in a public goods game. And so we came up with this decision heuristic that was roughly motivated by these papers, where we've argued that it is more likely for a richer individual, and by richer individual, I mean an individual whose wealth is larger relative to the average wealth of the neighborhood. And by poorer individual, I mean those whose wealth is smaller relative to the average wealth of the neighborhood. This is demonstrated in these figures. So the decision heuristic that we came up with was to propose that richer individuals, when they are embedded in a cooperative environment where 50% or more of their connected neighbors are cooperators, are less likely to cooperate, whereas poorer individuals in such an environment are more likely to cooperate. This is depicted by the blue S-shaped curve. Whereas in the other scenario, in a selfish environment, richer individuals are more likely to cooperate, whereas poorer individuals are less likely to cooperate. I mean, this was not completely random. There was a rationale behind this. In more cooperative environments, richer individuals, if they are driven solely by their self-interest, then it is better for them to defect because they can take advantage of the large number of cooperators, majority cooperators, to increase their wealth. Whereas poorer individuals are more likely to cooperate in a cooperative environment because they believe that by doing so, it'll increase the chances of them receiving more wealth because of the contributions made in subsequent rounds by other players. So with this decision heuristic, if you can go to the next slide. Yeah, so I've already talked a bit about this, so I'll skip this quickly. And the next slide, we carried out agent-based simulations where we took a group of individual agents. They were made to play a public goods game. And this figure shows a focal player, and the shaded region shows the nodes which are the neighbors of the focal player. So each individual is involved in K+1 public goods game once as a focal player, and the remaining K times as a neighbor of some other focal player. And in this example, in this figure, X is the focal player and it has two connected neighbors according to this network. And if you go to the other figures by clicking, yeah, so the neighbors change and the shaded regions identify the neighbors of the focal player. So this happens as a result of which each individual collects a certain amount of money from the public goods game, and the game is repeated over time. But at the end of each round, individuals are given the option of restructuring their connections as well, based on certain rules which are specified in the next slide. Yeah. So this followed closely the protocol that was followed by the experiment carried out by the Christakis group, where everybody is aware of each other's strategies and each other's wealth in one scenario. And individuals can choose to make connections with existing neighbors, break connections with existing neighbors and make connections with other members with which they were not previously connected. And these connections would occur with a higher probability if both individuals are cooperators. It would occur with a somewhat lower probability if one was a cooperator and the other was a defector, and so on. So the thickness of the lines connecting the two individuals denote the likelihood with which those connections can take place. And similarly, existing connections can be broken, and it's more likely to be broken if one of the interacting partner is a selfish agent. So based on these rules, we found using our decision heuristic that we were able to reproduce the results of the experiment. So this movie shows, gives a preview of how the network structure as well as the wealth of each node in the population is evolving over time. The larger the size of the node, the greater the amount of wealth that individual has. The color of the node represents whether that individual agent is a cooperator. In the case it's a blue node, or a defector in case it's a red node. And the restructuring of the network is happening, and you can see how the wealth as well as the strategies are changing over time. So this is how the game works, how the agent-based simulations were performed. So let's come to the results, so this is a result which shows how our decision heuristic is able to replicate the results of the experiments. On the left, we have the results of our decision heuristic in the two distinct scenarios, one where wealth is visible to every member of the group, and the other case where wealth is not visible at all. And we see that the invisible wealth scenario leads to lower levels of wealth inequality in the population compared to the visible wealth scenario, just like the experimental results observed by the Christakis crew. And so we went on to analyze these results in a bit more detail to try and understand how the microscopic dynamics can lead to such collective behaviors. And that can be seen from the next few slides. So let me talk about the overall results first, and then I'll go to the microscopic details. So we see two features here that are evident from the results of our simulations. The first is how the fraction of cooperators depends on the likelihood with which pairs of nodes are allowed to rewire, and how it also depends on the effect of the strategy environment on the likelihood of cooperation of individual members. So P0 is the quantity which determines the effect of the strategy environment on the likelihood of cooperation, and RE is the fraction of nodes which are allowed to restructure their connections. So the first thing that we observe from the figure on the left is that as the degree of influence of the environment increases, the probability of cooperation, the fraction of cooperators also increase. The darker color indicates higher levels of cooperation in the population. But the fraction of cooperators are unaffected if we allow the underlying network to restructure their connections. So there's no difference between a static network and a dynamic network. But in the case of Gini coefficient, the results are much more subtle, and the extent to which network restructuring helps in reducing Gini coefficient depends on the degree of influence of the environment on strategic cooperative decision-making. And when the environment has a moderate effect on cooperative decision-making, we find that making the network dynamic and increasing the fraction of nodes which are allowed to change their connections can lead to increasing levels of wealth inequality in the population. Whereas in the case where the environment has a more dominant effect, when P0 is larger, increasing the fraction of nodes which can rewire their connections leads to a drop in Gini coefficient, implying lower levels of wealth inequality in the population. So how do we explain these gross features in terms of the microscopic dynamics? So how am I doing on time? Do I have another 10 minutes, 10, 15 minutes?
10 minutes is fine.
10 minutes, okay, yeah. Okay, so, so if we can go to the next slide. Yeah, so as I already pointed out, there are these two features, and so this shows, the one before that. Sorry, the one before that.
Hang on, there's a little problem. Okay, one sec. Is this the one?
Yeah, okay.
Okay, all right. Sorry.
So this explains the impact of the strategy environment P0 on the fraction of cooperators and the Gini coefficient. So what we find is that as P0 increases, you can see from the figure on the right, it increases the propensity for richer individuals to cooperate in a cooperative environment, and but it decreases the propensity for richer individuals to cooperate in a selfish environment. So if you look at the blue lines, the lighter shades of blue correspond to higher P0 values. So you can see that in a selfish environment, the richer individuals are the ones to the left of the y-axis, because their wealth is larger compared to the average wealth of their neighborhood, and their probability of cooperation increases in a cooperative environment. And when the probability of cooperation increases in a cooperative environment, that increases the number of cooperative environments as well. So we have a situation where richer individuals are embedded in a largely cooperative environment with a higher inclination to cooperate. So this leads to more contributions to the public good, which when multiplied by the synergy factor and redistributed leads to lesser levels of wealth inequality in the population. And we can also see, and of course, higher cooperation fractions, as we can see by looking at how the number of rich cooperators and poor cooperators are both increasing over time as the impact of the environment encapsulated by P0 increases. So this is about how the environment affects cooperation levels. And so let's move on to the wealth inequality part in the next slide. So as I said, the wealth inequality depends on the level of influence of the environment on cooperative decision making. And in the first part, we want to understand how for moderate influence of the environment, increasing the probability of restructuring the network leads to increasing levels of wealth inequality. And the reason this happens is because as more number of nodes are given the opportunity to restructure their connections, if you look at the graph in the middle, top middle of the screen, you can see that the rich defectors increase as this probability of rewiring increases. And not only that, that has to be correlated with the graph on the top right, which shows that the cooperative environments are also increasing with increase in this rewiring fraction. And so when these two are taken together, we have a situation where nodes which are the rich cooperators are essentially the rich individuals are essentially embedded in a neighborhood where there are mostly cooperators. And since rich individuals are more likely to defect in cooperative environments, their contribution to the public pool diminishes. And this has a cascading effect, which reduces the overall levels of wealth that's redistributed to the population and increases wealth inequality. So this was the explanation for the moderate influence of the strategy environment, whereas for the other case where the strategy environment has a more significant influence on cooperation levels, we can see from the next slide how changing the rewiring fraction affects the Gini coefficient, and it leads to decrease in the Gini coefficient, which means lowering wealth inequality levels. And that can be seen by first looking at the figure in the top middle portion, where you can see that both the rich cooperators and poor cooperators are increasing in number when P naught is large. And so when both of these types of cooperators are large, both of them are embedded in cooperative environments. So the contribution to the public pool increases from both the contributions of the rich as well as the poor cooperators, and that leads to lower levels of wealth inequality. And that's captured in the values that you show here as you go down the column on the right. So yeah, so I'll skip the next step. So this is about the impact of the relative wealth. So I'll quickly go over the explanation before I move on. So here we find that when the influence, when the difference between the wealth of the individual and the average wealth of the neighborhood is not a factor, which is true in the case where the wealth of every member is invisible, then that corresponds to the case where you look at the top right hand graph. It corresponds to the case where the number of rich cooperators and number of poor cooperators dominate over defectors. So in the invisible wealth scenario, rich and poor cooperators both dominate over defectors, but as the wealth becomes visible through increase in lambda, the number of rich defectors increase. And as a result, most of these rich defectors happen to be embedded in a cooperative environment, and they pull down the wealth of the entire community, leading to larger levels of wealth inequality. So this explains the other aspect of the experiment of Christakis et al., where they found that visibility of wealth is actually detrimental to reducing wealth inequality levels in the population. And we are able to reproduce that from using this decision heuristic. So, yeah. So I don't think I have much time, so I'll probably not go over to the next part of the talk, but just to quickly give the motivation of the next part before I move on to the conclusions. So what we saw here was a scenario where every member, especially in the visible wealth scenario, had to acquire information about not only the actions of other members in the population, but also acquire information about wealth of the members in the population in order to use these factors in their altruistic decision-making strategies. But such information is often difficult to come by, and even if it's available, keeping track of the wealth and strategy actions of every member in the population, especially for large population sizes, can be quite heavy on the cognitive load, and it's not possible to process all that information. So this calls for strategies which require low information and yet are useful in terms of its ability to sustain altruistic behavior and maintain high cooperation levels in the population. And so we wanted to explore such a learning strategy that does not rely on extraneous information. And I don't have time to go into the details, so this was about the other half of the talk, other work which was done with Anuran. So I'll quickly, I'll skip these steps and go over to the conclusions because I'm out of time. So if you can skip over the results.
Yeah. Is that where you want it to be?
Yeah, if you can go to the last slide, I'll just talk a little bit about that.
Okay, let me try. I'm going in the wrong direction. Here, is this one?
Yeah.
Is this one?
Okay. So here, what we find is if we use a criteria which is based on an individual aspirations, which are dynamic, which can change over time, then it can be useful in not just sustaining cooperation, even though there are large fluctuations in the fractions of cooperators over the short time scale. Over the long time scale, cooperators indeed dominate for a large range of parameters. So this is a scenario where network restructuring is allowed, but restructuring is not based on information about either strategies or wealth of other members of the population. It is based on individual satisfaction levels and how those satisfaction levels are determined in terms of aspiration. So we have individual aspirations, and if the payoff that is received exceeds those aspirations, then an individual is satisfied. And that is an internal metric which individuals use to update their strategies over time rather than rely on information about the wealth and strategies of other members. And when they use such a heuristic, which is based on a reinforcement learning model, cooperation can be sustained for a large range of rewiring fractions. And so I'll end with the conclusions in the next slide. So what we find is often conventional methods used in evolutionary game theory has promoted the use of this pairwise comparison method, which relies on choosing a neighbor at random and imitating that neighbor's strategy, depending on a comparison between the payoffs of that neighbor and the focal player. But that is often not a very useful learning strategy when it comes to taking into account the complexities associated with which individuals take decisions on whether to cooperate or not. And a strategy that is based on both the strategy environment in which the individual is embedded, as well as the wealth of other members of the population, if that information is available, can be usefully incorporated into a decision heuristic and does explain results of behavioral experiments. And even in low information settings where such information is not available, a strategy which is based on individual aspiration levels and satisfaction based on a comparison of aspirations and payoffs can also be effective. And so these alternative learning strategies can prove to be quite useful in understanding how cooperation can be sustained in the population. So using this framework of the public goods game, of course. So I'll end there. And so final slide, I want to thank all of you who are here, and particularly Professor Shen for cooperating with me in terms of slide movement and ensuring that my satisfaction level has exceeded my aspirations, leaving me fully satisfied. Thank you.
Thank you. Thank you. This is a very interesting talk. I really wish we had more time, but beautifully delivered. And I hope I haven't completely messed up your, it was a little tricky because I'm not used to doing it. But let's go to the questions. I'm sure there'll be questions.
Suraj, could you go back to the conclusions and just put that one up, please? Thanks.
Conclusion, go back. Okay, let's see. Here. Yes. Is this the one you wanted?
Yeah, no questions. I just wanted to look at them.
Oh, okay, okay. Anybody has a question, you can unmute yourself and ask. Yuman, go ahead.
Yeah, I really appreciate this talk because one thing is that it can be used to describe current situation, right? Within the US and among the world nations, cooperation and not cooperation. And one of the book I read, but have not finished reading it, is something called The Price of Inequalities by, I think, Professor Joseph Stiglitz, who is a Nobel Prize winner in economics. And I think this talk may generalize to try to describe what is actually happened in the book from the physicist's point of view. Okay, and I think if it can be done, then the question is, in the book, he also provides a solution to the inequality of people's well-being. So the question is whether applying these methods can actually solidify the solution proposed by him.
Thank you for those encouraging words. I'm not familiar with the book, but yeah. I should caution that the scope of this work is somewhat limited. So I'll be a bit cautious about extending it beyond the domain where it's applicable. So our interest was on understanding social conflict, and a very specific kind of social conflict that's framed in terms of the public goods game. And inequality levels in the population has many different reasons, and it's a much more complex problem than understanding the kind of social conflict that is embodied through the public goods game. So those kinds of systems are very specific systems where contributions to a public resource help in the upkeep of the resource, whereas when more individuals start to defect on their contributions, renege on their contributions, the resource collapses to the detriment of all. Yeah, so those kinds of systems can indeed be better understood through modeling processes using agent-based simulations and carrying out behavioral experiments using online platforms like the Amazon Mechanical Turk. But it's a limited scenario. So the reasons for wealth inequality in the population are much more complex, and I would be a bit hesitant to extend the results of our work to that domain.
But I actually encourage you to do so in the future, because what happens is that in a certain group of people, there are always internal states, and the internal states are actually in conflict, right? And also the interaction, I mean, from the point of synchronization between different levels, sometimes the global, what we call the order parameter, will affect the synchronization within the underlying groups. And maybe sometimes they are not consistent, okay? So a synchronized state can develop into a desynchronized state and become chaos at some sort of time.
It's an interesting point you raise, actually. I had a similar point, but I think Shomi also wants to ask a question.
Yeah.
No, go ahead. I mean, sure, feel free to go ahead. I mean, you don't have to.
No, you go ahead first, and then I'll come back.
Okay. So Supratim, I mean, despite your attempt to keep it at a very kind of rigorous level, those of us on the screen are kind of drag you back to the social focus of it. So, I'm looking at your conclusions, and the last one seems to me to give me great cause for pessimism, right? Because I mean, if you look at it, you're talking about low information settings, cooperatives can dominate. Now, if anything, this is about the highest high information setting we are in of any time, especially in terms of social media, the one-to-many, anybody can say anything non-cooperative and immediately. So are we entering an age where the smoochers will take over the world as opposed to the givers, and the non-cooperatives will come to rule, as we are seeing now? So if the last statement is true, then it seems to me to be a very pessimistic outlook.
Definition of Kali Yuga.
You may have access to the information, but you don't need to use it, right? And so too much information is a problem, and it's a bit unfortunate that I could not, I did not pace my talk well enough to go through that part of the talk in a bit more detail. But what that suggests is actually a source of optimism for me, because it says that, I mean, even if you don't have if you have information, of course, it gets more complicated. How do you use that information about wealth, strategies, and other factors of others? But even if you ignore that information and choose to cooperate based on some internal metric, which can be dynamic. It's not that internal metric, that aspiration level that we set, is a static one. It can be a dynamic one, and it was a dynamic one in the work that we did. It does help cooperators to proliferate, and if not proliferate, even and not get wiped out and by defectors in many situations, and except for a very small number of cases where which are not really realistic. So that gives me hope rather than rather than making me despair.
So Supratim, in response to you, I'll make a Bengali statement which you will then translate for the rest of us on the screen, which is Tomar mukhe phul chandan poruk.
May you be blessed with flowers and sandalwood. That sandalwood whatever mix. I have a few questions. One was, is it possible to think in terms of a relaxation time for the altruists? So altruists can become a a selfish person after a certain time.
Right, exactly. Yeah. So if you are willing to go back a few slides, I can answer that question.
Let's try that
more convincingly. Yeah. So let's go to the next slide.
Next, meaning forward.
Sorry, forward. Yeah, this one.
Okay. Okay.
Yeah. So this one suggests that so the x-axis on the two figures on the right is essentially time, and so in this work, what we find is individuals can change their strategies on very short time scales, right? So they, I can choose to cooperate, and in the very next round, I choose to defect. But if we have a situation where we are in a network where during a large enough period of time, we are connected to other cooperators, and the cooperator-cooperator links are sustained for longer periods, then that can be leveraged to increase the payoffs to exceed the aspiration levels and ensure that cooperation dominates over longer timescales despite large fluctuations over short timescales. So, yes, so you can have large changes in behavior from selfish to altruistic acts over short timescales, but if certain conditions are satisfied, if cooperators can leverage connections with other cooperators over a sufficiently long period, then cooperation can be sustained. So one small feature that I would like to point out is this black line you see, which is creeping up slowly in between the regions. So that gives the number of links between cooperators and selfish agents. And that link is creeping up slowly, which means that over time, the collapse of cooperation is brought about because more selfish agents are connected to cooperators and they start exploiting them and reducing their payoff, which drops below the aspiration levels, and that leads to a cascading decrease in cascading failure in the overall levels of cooperation. But then that cycle repeats, and that's the good thing about it, right? So overall, in the long time scale, it's beneficial for cooperators.
For a while, it was making progressively lower lows, so I was getting worried. But then I see it's going up around 740 thereabouts. So it's like, so it's like a this stick slip type behavior. I have a second observation I wanted to make. When you look at Wikimedia, right? So that's the founding body that runs Wikipedia. Wikimedia, they always say, that when they fundraise, they say, how many people actually contribute. This is a fantastic example of altruism because everybody uses this thing, and their claim has been for a number of years that the number of contributors, people who give money more than like $2, is 2.7% of the population, 2.6 to 2.7% of the population. So I was thinking this must be some kind of equilibrium number that you are hitting, because this is averaged over decades now, and it is essentially a population of people who can expend money in dollars. Typically, probably $10, $15, $20 is not a big deal to them, and they contribute. And if you take that kind of restricted set of people into account, you probably get this number. And I was just wondering if you have seen any evidence of this. Yuman, you have a comment on that.
I think this 7%, 8% is what people call the power law, right? 20% of people doing 100% of the work.
Yeah, this is 2.7%.
No, but the exact number is not important. The important is that the minority of the population is doing most of the work.
Yeah.
Right.
Yeah.
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 This happened when I working in a project, right? In the beginning, you spend 1 month, you complete 90% of the project. But they took a year, 2 years to finish the project. Okay.
Tail off.
And,
yeah.
so,
there is a long time tail here that comes out.
Yeah. So all social behavior are observing this hierarchy level of behavior.
Yeah, I'm just curious if you see it though. I mean, he might be able to see it with simple rules. That'll be really cool.
But I think these numbers also depend on the size of the population, right? So in a family setting, this 80-20 rule does not apply because it's not like one member of the family does everything for. Whereas if you go to villages in the traditional setting, and these studies have been done, it is much more egalitarian in terms of workload distribution. But of course, if you go to large populations, especially anonymous populations, such as the Wikipedia readership, then maybe there is some kind of distributional law that settles at some low percentage that you mentioned. I mean,
I think the power law arises from the multi-level of interaction, not just the population of the same. If you have homogeneous population, it's
some kind of hierarchical hierarchy of interactions.
Yeah, there has to be at least 3 levels of things interacting across levels to give you this power law.
Okay. That'll be interesting to check because it's got to be, Horace, go ahead. Sorry, we have been dominating the conversation.
That's all right. Thank you very much for the wonderful talk. There are a lot of interesting stories about Benjamin Franklin. And one of them is that he used to promote and tell people that if they want to be successful, they have to get along with people. And that's a nice story. But unfortunately, he could not get along with his son.
But there's just one level.
Yeah, thank you for the comment.
Thank you.
Yeah, this is actually like a Van der Waals interaction. You have to have a common glue, right? A global Van der Waals attraction, for example, which is what you need for a mean field theory of your.
I think it depends a lot on the system size because our focus was on trying to understand these behavioral experiments. And these behavioral experiments are typically conducted with a fairly small population. The one that I mentioned by the Christakis group was performed with a population size of on the average 20 people. They repeated it. They had several replicates of 20 of sets of 20 and repeated the experiments on these different sets several times to get better statistics, but the group size was quite small. And typically in large groups, there's a different dynamic which enters, and it usually depends on, so you don't have information about what others are doing. And it usually depends on how you are influenced by one particular neighbor because he or she happens to be your close friend with an opinion, and that can trigger the decision-making process.
Yeah, this is the hierarchy issue that actually Yuman just brought up, right? We have hierarchy of interactions rather than
right. And the influence also. I mean, what we did not do here was to work with weighted networks where each individual would have a certain level of influence on others that he or she is connected to. And I think that's an important factor.
Yeah, that's a great point. That's exactly something I was thinking that you value, for instance, somebody you're very close to, that person's judgment or less, as opposed to a random person. We tend to have different
right
importances associated with the interactions, right? I mean, If my student says something when I'm teaching a class, I take it very seriously. But if my colleague says, I probably take it less seriously because that person is not in the class. Whereas in something else, that colleague may have much more influence on our decisions. And yeah, so it's a very nuanced and context-dependent way in which human interactions proceed. But this is a fantastic topic.
Following up on it, I wonder if we're entering an age where that kind of isolated study groups, if you will become more and more difficult. I know, for example, biologists have, when they do genetic migration pattern studies and so on in the past, as recently as 50 years ago, they could go to individual populations in Papua New Guinea, for example, or South Africa, and study population groups which were essentially had been isolated for, God knows how many centuries, and the gene pool was, not diluted and so on. That sort of study would be essentially, unfortunately for them, impossible to do today, because you cannot find any population anywhere which has not had some strands of, especially, and so it could be that these kind of, when you talk about, groups of social interactions, I mean, if you compare, let's say, an average teenager 50 years ago and the number of personal interactions they would have had in the course of a day, and then fast forward to the age of Instagram, and the average interactions you're having in the course of a day with people who are commenting on, let's say, your physical appearance or something, that ship has sailed. And so I wonder if the scenario of small groups where the nodes are closely connected but isolated from the rest of we're entering an age where that is just not going to be the case anymore.
You could try your luck with cannibals.
I mean, that's right. Even on social media, in fact, there have been cases where people have got into that because they read about it on somebody else's post.
And they've gotten eaten. Exactly. I heard about some of those too, especially in the Andamans, for example.
So I think the nodes, there are just way too many nodes is the issue, I think.
A lot of nodes. I think it is very late for Supratim, so we should let him go.
But I mean, just to comment on that point, I don't think it's a matter of whether we can isolate or the validity of these results depend on whether we can consider isolated groups and do experiments on them. Cooperation typically exists thrives only in small groups. I mean, nobody talks of cooperation. I don't know. It depends on what you mean by cooperation also, but here I had defined cooperation in a very specific manner in terms of sustaining a public good. So, but it's more difficult to talk about cooperation at the level of nation states or institutions using the framework that I have been using.
There you have the tit for tat strategy. That's your nuclear strategy anyway.
Yeah, that's scary. Yes.
Don't tell your thesis to Zuckerberg, who's claiming that 6 billion people are cooperating in a wonderfully benign way on his platform.
We are going to have a lot of fun with this one. This is a fantastic topic of discussion. Thank you so much, Supratim, and thank you for everyone for relaxing with us post-talk. Happy New Year in case I don't see you before that.
Yeah, thank you.
We'll try to squeeze something in, but maybe we will meet in January again.
Thank you all.
Yeah.
All right. Bye-bye. Bye. Thank you. I have to see how I end the meeting because this is a completely new setup for me. Okay, there we go.
Yes.
All right.
So can I ask you, Professor said, have you written the paper for Professor Kenkri yet?
I'm writing it. I'm one of the last ones who hasn't done it yet. Actually, there are 2 or 3 papers still missing.
Okay.
But yours is out for review.
Yeah, I read Bokesh one, the first part.
Yeah, very nice papers have come, but we are making excellent progress. I think we'll be
so
done
many
very
results.
soon.
Yeah. So
many
results.
Yeah. All right. Bye, Yuman. I will run.
Okay. Bye bye.
Take care. Yeah. Bye.